Okay, guys, welcome. Today we're going to talk about Euler's phi function. Now, when we studied modular arithmetic, we looked at elements of Zn and whether or not they have a multiplicative inverse. And of course, we know that that question has an inverse only if the equation a times x congruent to 1 mod n has a solution, right? So we want to find a particular x such that this is true. Now, of course, this only happens if ax minus n times y is equal to 1 has a solution, which of course is only true if a and n are relatively prime, where the GCD of a and n is equal to 1, right? So the elements of Zn have a multiplicative inverse, are the elements of a, are the elements a of Zn that are relatively prime to the modulus n, okay? So what we do with Euler's phi function is for each positive n that's greater than 1, phi n is the number of positive integers less than n that are relatively prime to n, right? So for example, if you look at phi of 6, that would be 2. Excuse me. Since the GCD of 1 and 6 is 1, so there's 1. But then the GCD of 2 and 6, 3 and 6, and 4 and 6 is not 1, so we skip them. And then the GCD of 5 and 6 is 1. So that gives us two numbers that are less than 6 that are relatively prime to 6. So phi of 6 is 2. Now, a couple of theorems that we'll need for this are for any prime number, phi of p is p minus 1, right? Because all the numbers up to p would be relatively prime to it since it is prime. So we get that there's p minus 1 of them. Now, using sort of a counting argument, you can show that if you have a prime to a power, phi of p to that k is p to the k minus p to the k minus 1. Right? You can use a counting argument for that, but we'll skip that here. And then finally, if a and b are relatively prime, then phi of a times b is equal to phi of a times phi of b. And of course, to make use of these theorems, we need the unique factorization theorem, or I think earlier I called it the fundamental theorem of arithmetic. And this just states that for any number that you have, you can factor it uniquely as the product of primes. All right. So for example, if we want to find phi of 100,000, how many prime numbers are there that are less than 100,000? Numbers that are relatively prime to 100,000, less than it. We know that 100,000 is 10 to the 5th, which we can break into 2 times 5 to the 5th, which is then 2 to the 5th times 5 to the 5th. Now, since 2 to the 5th and 5 to the 5th are relatively prime, from this step to this step, we're using the fact that phi of AB is phi of A times phi of B for AB relatively prime. Okay. Well, then at this point, we can then take our primes to those powers, and we know that the phi of prime to a power is p to the k minus p to the k minus 1. Right, so then 2 to the 5th will become 2 to the 5th minus 2 to the 4. Well, I should say 5 2 to the 5th will be 2 to the 5th minus 2 to the 4th. And phi of 5 to the 5th will be 5 to the 5th minus 5 to the 4th. So if we do some algebra, we'll be able to factor out a 2 to the 4th, and we'll be left with a 1 because we'll have 2 minus 1. And then a 5 to the 4th times a 5 minus 1, so times 4. So then if we multiply all this stuff and put it back together, we'll get that phi of 100,000 is 40,000. So there are 40,000 numbers that are less than 100,000 that are relatively prime to it. Okay, now let's do the same for phi of 172, given that the prime factorization of 172 is 2 squared times 43. Well, we'll break it into, of course, 2 squared times 43. And then since 2 squared and 43 are relatively prime, we can separate them. Now phi of p to a power of a prime to a power is 2 squared minus 2 to the 1st. And if we just have phi of a prime, it's just that prime minus 1. So we get 2 times 42. So there are 84 numbers that are smaller than 172 that are relatively prime to it. All right, so that concludes this video on Euler's phi function. I hope you enjoyed, and I will see you next time.